Okay, so we're doing a wee introduction to the binomial theorem. This is part 2, so we've had a look at Pascal's triangle, and we're about to look at some of the operations that we're going to need to learn about the binomial theorem topic kind of for real. As well as Pascal's triangle, what you need to be able to do is to understand about the factorial operation. You've maybe seen it before, the little exclamation mark. It doesn't mean that it's a surprise or that somehow we're having a party here. It just is a mathematical symbol for a particular calculation. So 4 factorial, as it kind of says here, 4 factorial is calculated by taking that number 4, and then we're going to multiply it by the next number down, whole number down, 3, multiplied by 2, multiplied by 1, and that's our answer. And if your mental mathematics is pretty good, 4 times 3 is 12, times 2 is 24, multiplied by 1 is 24, so the answer is 24. 7 factorial is exactly the same idea. We can say that 7 factorial starts with the number 7, and then we multiply by 6, then 5, then 4, then 3, then 2, and 1. A wee bit more of a calculation if you wanted to start from scratch. We can use a little bit of information in the sense that we already know that the numbers up to 4, so 4 factorial is here. We know that's 24. So if we start at 24 times 5, that's 120, and 120 times 6 is 720, and so if we work out the answer to 720 times 7, we would actually get the answer, and you can either do that in your head, or you could work it out. 0, 14, 50. So the answer is 5040. Okay, so a factorial operation always uses a positive integer, and we multiply that number by every other number below it down to 1, and then we stop. Okay, so in general, what we say is that n factorial is represented by the number n, so we always start with that number, multiplied by the number 1 less than n, times the number 2 less than n, and so on, until we get down to 2 and 1, assuming that n is kind of bigger than 2 in this kind of situation. That's a kind of general rule. What happens if we've got bigger numbers, or we need, in this case, to work out numbers quite quickly? Well, there's a button in your calculator that will do it for you. On the Casio calculators that a lot of people have, you'll find it as a shift function button. You're looking for the button that says x to the power -1. I'll write that down in just a moment. So you're looking for the button that says x to the power -1. It's on the right hand side, just underneath the blue button, and it's actually the second function of that button. You'll see it says x factorial. So have a look for the button somewhere. So in order to find 6 factorial, all you need to do on your calculator is do second function, and in fact, no, press the 6 first. Now you do 6, and then second function factorial equals, and it gives you the answer 620. So all we need to do initially is just to put the number in a calculator. So this is a little exercise for you just being able to do it on your calculator. So if you want to stop the video, and if you want to try finding the other two first, and then you can check up with me. So 10 factorial on the calculator, put in the number 10, shift x to -1 there is 720. Well, that can't be right, because we just said 6 factorial is 720, 10 factorial is, whoa, it's a big number. Okay, so we've got 3, 6, 2, 8, 8, 0, 0. See, all of a sudden, we've got this very large number because we're doing multiplying each number in turn by the next biggest one. So factorial numbers get very big very quickly, and if you want to see how quickly it does get, 25 factorial is actually crazy large. Okay, at 1.55 times 10 to the power 25. Wow. Okay, so we don't tend to deal with numbers that big. We're dealing with small factorial numbers, but it's good to be able to use it on your calculator. There's lots of applications of factorial operations in a whole lot of mathematics. I'm sure you'll come across a bit more of them later if you study more maths. Interesting one. We're going to need to know what is 0 factorial. Well, according to our definition, there shouldn't be a 0 factorial because we're multiplying and we end up down at times 1. In other words, we can't start at 0, but for the purposes of our kind of algebra or theory of it, we need to have a value for 0 factorial. And the way we kind of justify that in our minds is we do this. We think about the idea of wee patterns. If I were to say to you 3 factorial is 3 times 2 times 1, it's actually 3 times, well, 2 times 1 is actually 2 factorial. So in other words, 3 factorial is the number 3 times 2 factorial because, as you can imagine, that is all the other numbers down to 1. Okay. In the same way, we could say that 2 factorial is the same as 2 times 1 factorial. 2 times the one below it factorial. Okay, 1 factorial is just 1. And it means that 1 factorial then, which we know the value is 1, has got to be 1 times 0 factorial in theory. Okay, so look at this last one here. We know that 1 factorial is just 1, and we know that 1 is something. So the question is, what's the value here? What's 0 factorial? Well, in order for this equation to hold true, it has to be the number 1. It has to be a 1 that goes in here. So we can say that 0 factorial has the value 1. And that's a kind of theoretical value that we're going to have to use from time to time if you see that coming in. It doesn't kind of make much sense, but sometimes in mathematics we have to follow a pattern even if it doesn't make much sense to our kind of tangible brain. Like some people aren't very good at dealing with negative numbers because they can't hold negative 2 apples in their hand because their concept of number is about what they can hold or count. So, you know, there's a sense by which we have to just be a wee bit theoretical at times, okay? Now, here's just the last thing we're going to have a look at. We can actually, without working out, we can simplify factorial fractions by thinking about that quality that I just talked about. So, for instance, 4 factorial divided by 3 factorial, we can rewrite this as the number 4 multiplied by 3 times 2 times 1, which is 3 factorial. So in other words, 4 factorial is just 4 multiplied by 3 factorial divided by 3 factorial. Now, it stands to reason that 3 times 2 times 1 is a factor on the numerator, 3 times 2 times 1 is a factor in the denominator, so we can divide through by that, which leaves us just with, effectively, the number 4. So the answer to that is 4. I could have worked out 4 factorial is 24 divided by 3 factorial, which is 6. 24 divided by 6 is 4. But again, with like in all division and multiplication, simplifying first is always good. When it comes to the second one here, it's 7 factorial divided by 4 factorial is 7. Factorial is 7 multiplied by 6 times 5 times, and then here we get to 4. Because I've got 4 factorial on the denominator, I can say times 4 factorial, and I've got my wee dividing line divided by 4 factorial. So again, we can divide through by the factor of 4 factorial, which leaves us with a simpler calculation to do, which is just 7 times 6 times 5. 5 6 is a 30. 7 multiplied by 30 is 210. Okay, now they're kind of numerical applications. Oops. Can we bring that down here? We'll get rid of that. We'll bring this one down as well. So let's have a look at these two ones here. We can apply algebra in exactly the same way, of course, as we can apply our numbers. So we've got n plus 2 factorial divided by n factorial. So the numerator, we can say n plus 2 factorial is just the top number, which is n plus 2, multiplied by the next number down, which is going to be n plus 1, multiplied by the next number down, which is n. And because we've got n factorial on the bottom, we can just say times n multiplied by all the other numbers below it. Okay, just exactly as we did with the numbers up above. We're going to put our wee division line, whoops, and we're going to put n factorial here. They cancel out. Sorry for that horrible line. In fact, I'm going to, in case I get hauled up by my students, I'm going to draw a line. There we go. I have to be seen to be practicing what I preach. And we're going to do n factorial. We're then going to divide through by n factorial, and we end up with just what's on the top there, n plus 2 times n minus 1, which I could multiply out, but I'm not going to just now. I'm just going to do that. There's your answer. And the last one looks a bit more complicated. We've got numerical factorials, we've got algebraic ones. So we can take the 5 factorial and the 2 factorial there, and we can say that because 5 factorial is bigger than 2, we can kind of deconstruct 5 factorial all the way down to 2 factorial, which isn't really simplifying it very much, to be honest. Let's get a little line in here because I'm going to need it. We're going to have lots of things going on. And what have we got? So on the denominator, we've just got 2 factorial. And then we're also got n factorial and n minus 3. Now remember that we always deconstruct or decompose, if you want to use the bigger number. You notice 5 factorial is bigger than 2 factorial. N factorial is bigger than n minus 3 factorial. So again, we've got kind of n minus 3 factorial. So what we have to think is up here we've got n times n minus 1 times n minus 2 times n minus 3 factorial. Okay, I've just squeezed it in there. I'm going to extend my fraction. So what we can do is we can cancel common factors. We've got a common factor of 2 factorial. We've got a common factor of n minus 3 factorial. They all go to 1. And we've got, what remains is a numerical factor of, we've got a numerical value 5 times 4 times 3 is 60. And that's all the numerical values. We've got n times n minus 1 times n minus 2. So I could go ahead and multiply it all out, but I'm just going to leave it in that kind of form there to make the point that we can simplify fractions with factorial operations just by splitting up one factorial into its first few multipliers plus a lower factorial. So I hope that makes sense. So we're going to go on and have a look at the binomial theorem, the coefficient formula in the next example. So hopefully this introduction has been helpful, because you'll need these skills in what we're about to do. And you're looking for example 0 is the first example. Okay.